Okay, section 9.5 is something called the Doppler effect. This is the last section of chapter 9, so hooray, you made it. Now, you've probably all heard the Doppler effect before, but just in case you haven't, I'm going to try and play a little video here. I don't know whether it'll work with the sound, but we're going to try it. Okay, so now hopefully that sound came through and you could hear before the fire truck got to you, it sounded one way. When it was right at you and then past you, that sound changes, and there was an audio point that just it switched. Okay, so that's the Doppler effect. So what it is, in a nutshell, is you have a sound source, okay, that's moving, and the movement of that sound source creates different effects in front of and behind its movement. So you can see here with the fire truck, you can see in this area right here, all of those sound waves are more compressed. Okay, so they're tighter together because the truck is driving to the right as its siren is blaring. So those, if you want to think of them as crests, are more crushed together. The distance between them is crushed together. So it gives off an apparent or a higher frequency to a stationary observer. To someone behind, sitting back here, they don't hear the same compressed waves. They hear waves that are more spaced out. Okay, and so that has an effect on what they actually hear. So here's a different look at it, same sort of concept. Okay, so this one here, A, is a stationary source, so the sound goes out in all directions. Everything's equally spaced. This B version is an object that's moving to the right. Okay, and you'll see again, here's that compression. So you would have a higher frequency in front of this object and a lower frequency behind the object. Okay, so now, not everything, if you walk past someone while you're talking, you won't experience a Doppler effect. There's a certain fraction percentage. You have to be moving quick enough to make this happen. Now, if you were running at your full speed past someone and you were screaming, they might be able to hear enough of a Doppler effect that they can say, hey, I heard it. So there's your homework for the weekend. Go out and run past somebody in your household or your neighbor screaming at the top of your lungs and see what happens. Kidding, kidding. Okay, there is one little calculation that goes with this. And it looks quite complex, but don't worry, it's not that bad. Some of the subscripts will go through. So this is the frequency of the observer. Okay, so this is what someone listening, that's the person standing on the sidewalk with the fire truck, this is what they hear. Okay, this F naught or F original, this is the original frequency. Okay, so say it comes out of the siren at 400 hertz, the observer might hear 500 hertz. And so we have to sort of justify how does that happen. Okay, and there's one other key piece. For grade 11, we keep the velocity of the detector stationary. Okay, so in this course, this value right here will always be 0. Okay, so the velocity of the detector will be 0. In future courses and other things, you might have that detector moving. That changes a few things. But for what we're going to look at, that velocity of the detector will be considered to be 0. I'm going to highlight this little expression here. We'll go back to it in 2 seconds, but this is not the way I learned, so I want to just go through this. The frequency that's observed is equal to, and I'm just going to go V sound over V sound, and I'm not going to put a plus or a minus in there. And then I'm going to put source, and then I'm going to put the original frequency. Okay, now I like to sort of think my way through these. I don't like to try and memorize, as I've commented many times before. If I am standing in front of a source, okay, and I am the observer down here, I'm expecting a higher frequency. Okay, so if I want this calculation here to output a high frequency, okay, so I need this side here to be greater than this side in terms of the frequency. So the observed frequency is going to be the original frequency multiplied by something greater than 1. So if I look at this expression here, if I have the velocity of sound on both top and bottom, okay, if I add or subtract the velocity of the source from that, I have to create a number that's greater than 1. So if I want this to be greater than 1 so that I get a frequency that's higher than the original, then I have to subtract. Okay? Because if I say, let's put some numbers in here, say the velocity of the sound is 100 and this is 100, and if I say, let's put this as 10 for the velocity of the source. Okay, now I have a smaller denominator than my numerator, so that should end up being greater than 1. Okay, and that means my frequency, when I multiply my original frequency by a number greater than 1, it should go up, and that would be the observed frequency. So when an object is out front and the source object is coming towards you, then you want to use a subtraction in that formula. Okay, now if you are behind, say, let's go change this to blue. If you are behind and these frequencies are farther apart, okay, then you expect the original frequency to go down. Well, if I want the original frequency to go down, I do not want to subtract the source. I want to add the source. So let's do that again. See, so now if I have 100 on top and 100 on bottom, but I add 10 to it, that overall multiplier in front of the original frequency will be below 0 now. So now it will be less than 1. So it will bring my frequency down, and that's what I would hear over here. Now if you want to look at this little sentence, they have I'll highlighter it for you. When using the equation, if the source is moving toward the detector, the speed of the sound is considered to be negative. Okay, we just talked about the mathematics of why that would work. If you're a memorizer, you're welcome to memorize. If the source is receding from the detector, so that's the behind case, the speed of the sound is considered to be positive. If you want to memorize it, go right ahead. If you think about it mathematically, though, it makes sense on whether you're going to add or subtract the source to it, depending on whether you want to create a higher frequency or a lower frequency. So let's have a quick look. A fire truck is moving toward a stationary observer at 25 meters per second. The frequency on the siren is 800 hertz. Calculate the frequency detected by the observer as the truck approaches and the frequency detected by the observer after the truck passes by. So we're going to do the before and the after. The speed of sound in this case is 342 meters per second. Okay, and you'll notice the source is, they've put in a negative already. The detector is 0, as stated, we'll always have that. So we have two cases. So let's do the first one. So the truck is approaching. So if I'm approaching, if this is the fire truck and I'm standing here, I'm expecting that frequency to be greater than 800 hertz. That's my expectation. So when I go to solve this, the observed frequency, the velocity of sound is 342 plus 0, 342. Now again, I can try and memorize it. I just have to think this through. If I want this to be greater than 800 hertz, which is the original out here, I don't want to add 25 to this. I want to subtract 25 to this. And that's really important. Okay, so if we do 342 divided by 342 minus 25. Okay, and then I times that by 800. I should get 863, whoops, that's a really bad 63 hertz. Okay, and that makes sense. So let me just fix that. That's a really bad 3. Okay, now I'm not going to do the second part. Okay, the second part would be if you're the person that's behind. So the only thing that would change is instead of adding 20 or subtracting 25, you add 25. Okay, so let's do it. Why not? We're here. So frequency observed. So 342. Now we do plus 25. and our original was 800 when we punched that all in. So 342 divided by, what's that, 367 times 800, and I'm expecting a number less, 746 hertz, which is what I get. Cool. So it's not a hard equation to deal with. It's really just understanding on where you are in terms of whether you're going to add or subtract the velocity of the source. Okay, if you want to pause it here and try a couple, there's 2 questions here to try. Okay, so in the interest of keeping this relatively short, so a police car is approaching at a speed of 20 meters per second with its siren emitting a frequency of 1000 hertz. Be mindful of that prefix. What frequency does a stationary observer detect? The speed of sound in this case is 330 meters per second. Okay, so if we are approaching, that's the key word. So that means we are standing out front of the police car and it is going that way. So without doing any calculations, I know I better get something bigger than 1000. Okay, so they got 1100. Okay, so that makes sense. An ambulance has just passed by your home. You detect that the frequency of the receding siren, see, this is a little different. The frequency of the receding siren is 900 hertz. So this isn't what the original is. This is what you observe. Okay, so that's the other side of the equation. If you know that the frequency of the ambulance siren is 950 hertz, okay, how fast is the ambulance moving? So let's set this one up just for argument's sake. So we have observer, we have velocity of sound, velocity of sound, velocity of source, and we have frequency of the original. So we know this is 900, this is what we observe. We know that the speed of sound is 335 plus the velocity of the source, and we know the actual original, okay, is 950. Okay, so now to solve this, you have your unknown in the bottom, so we've got to do some math here. So I'm going to divide both sides by 950. You don't have to, this is just one way to attack the problem. That gets rid of those terms. I'm going to be a little bit lazy and get that all together. Okay, now I really want to get this piece out of the bottom. So I'm going to multiply both sides by that 335 plus V source. So this becomes 335 plus V source, all in a bracket, times 900 over 950 equals 335. Okay, now once we're at that stage, now it's a bit of, if you want to say cross multiplying, you can. We're not going to touch this bracket just yet though. This is 335 V source. Okay, and then the other side we can do some cross multiplying. I can't believe I said that, but looks like that. Okay, and then the last step will be you'll subtract 335. This is all one piece. You'll subtract that from both sides, and we should end up with a V source. Oh, let's just switch to purple here. So we'll go 335 times 950 divided by 900, subtract 335, and we should get 18.6 meters per second is the velocity of the source. And if we on 18.6, so there we are. So the key part in this is you have to remember to keep this, come on yellow, there we are. This is a package deal. You have to bring the whole thing up. Okay, so there's a quick summary. You can pause it and read over that, and then we'll finish with section 9.5. 2, 3, 4, 5. So I didn't write that in. 9.5, 2 to 4, and 6. And then if you're interested in reading, this is a really fun section. There's a couple of links here as well. Rogue waves. Yeah, just a really interesting nautical combination of these ideas.